That's all right.
It is recorded.
Yes, it is. So good morning. It looks like we're about 2 minutes late now just because of the technical difficulty, and I apologize. I was supposed to press a button that looked like an off button to turn it on. This talk is a pivot of a previous talk I'd done where I was basically talking about a number of the tools that I'm discussing here briefly. And instead, I decided to focus on what are the actual problems that motivated these tools to be created in the first place, and then so I'm situating those tools in the context of where they originally came from. So this is just a series of production outages and some of the things that I used while debugging them and what the resolution was. These go back a number of years, so I've a number of the details for some of these things I've forgotten, but the rough outline I still have. And of course, the tools are on the internet, and you can use them. Furthermore, everything that's actually in this talk, this is nothing in the slides is original information. You can get everything else from CPAN or blog posts or anywhere else on the internet. While you can, of course, download the slides, and you can take notes on this if you feel like, but you won't miss anything if you just get the highlights from this as well. So the outages specifically, these are the several that I thought I would just run through quickly. Yeah, that seems ambitious at this point. Some of the last ones are small. So that's what you can look ahead to. The first one, this is an outage I was dealing with on Monday where I had a series of forked processes. They deadlocked around reading from a pile of file handles to and from each other. And this is a code base that I was really unfamiliar with, but had to fix anyway. This is, in fact, a Python code base, which I don't write Python either, but have to deal with it. It's still a reasonable Unix process, C process, and this is actually very similar to how Perl works. So with that respect, it should map very well to what we have here. So I had no actual recent changes to the source code tree, so I could rule out things like, were there any changes I could look at and get? For ordinary debugging issues, I really want to start with, has anything changed recently? Has something caused this? In this case, no, actually. I think the servers woke up one morning and did it. It's actually, I don't know, I don't have a root cause on this thing yet. It's very strange. But when I looked at the thing in top, what I could see is all the processes I was expecting to see actually doing work were doing absolutely nothing. If I looked at netstat, you could see a lot of connections that I think were in like TCP wait or something like that. Actually, one of the ops people told me what netstat said. I didn't look at it myself. Where I went from is I looked at PS tree, because again, this is a process I wasn't very familiar with, to go ahead and understand what is the structure of this thing and who are they talking to and why. And so I could see, all right, this is effectively a supervisor that's talking to a series of worker nodes, and they're passing information back up and down to each other, and something's not going wrong, or not going correctly. I took each of the process IDs from this list, since these processes were doing nothing that I could tell. I S-traced each one individually, and I could see that most of them were waiting on some kind of lock, futex. One was reading on a wait, one was reading on a write. There's another one waiting on, actually I was waiting on another process. From there, I knew a series of file handles. So I could look up my file handles using LSOF. And since I still didn't know what was going on, we ended up actually stepping in through GDB to see what was going on. So how we did this was one of the processes, when I pulled up strace and pulled up the process ID, this is effectively what I saw on the ones that were actually interesting. And there's a lot that said they were waiting on some futex. Most of them were waiting on a 32-bit pointer for futex, and 2 were waiting on the 64-bit. So I think that's some shared lock, I guess. I don't know. But what I did find was really interesting. So I could see the wait for was waiting from a supervisor to one of the children. And those read and writes, those numbers next to them are the file handles, which with other information in the system, I can index back and find out what those actual handles are and where they go. So explaining that, if I ran the LSOF command on the process, I can get the list of all the files that are opened by that. So, for example, on the LSOF command, the read for I can see that, oh, that's a pipe going to somewhere. And the identifier that's left of the pipe, I could correlate back to some other process or some other line somewhere else that was reading from it. Or what I actually did is, in this case, you could also look at the proc file system, and the number 4, again, actually shows up as a symlink to something. If it's a socket or if it's a pipe, then I guess it's just text. I don't, I mean, when I ls-l, things like network, I see symlinks to things that look like text that aren't actually files, but it's really informative. And I can still take that identifier information and go back and tie back to where it's actually coming from. But since I hadn't solved the actual problem yet, this is very similar to my actual stack trace. It's not the literal same one. I just sort of I copied something reasonable in for this. This was not helpful to me in terms of helping me solve the problem. Well, what it did help me rule out is it helped me rule out things like, is there some C library that's causing some strangeness? What I could see is if I was effectively terminating in Python code. If you do this to a Perl process, you'll see it terminating in a series of Perl function calls, and generally not something that comes from some libxml or whatever. I mean, it'll be very obvious if it transitions and goes off to some other library, and then you can begin suspecting there's something wrong with that, possibly. What actually sort of solved the problem for me and allowed me to cease having an active outage. I'm still in a brownout condition at the moment, and I'm still actually working on it. I don't know when I'm going to be done. But for, say, Python or for Perl, there are similar tools that allow you to go ahead and generate GDB scripts that can extract the real application stack trace. So for Python, there's a URL, and you can ask the internet for exactly where to get the pystack code. It's effectively just a I believe it actually requires your Python to have symbols, so I had to install the optional package for that. You'd have to do a similar thing for Perl. There's actually another option for Perl, which I've written called app-stacktrace. It installs a script called perl-stacktrace, which you may either give it a process ID, and it will read a memory image and give you a stack trace directly out of it without symbols. Or you can use the -m parameter, and it'll just generate a Perl script, generate a GDB script that's useful and does effectively the same thing. The way that might look is I could take that script I just generated, and I could just pass it directly to GDB, and I would get a stack trace directly back off of my production process. And I do not require symbols for this to work. And just the paragraph below that is effectively how the Python code would have worked. So that was what I actually did. So the solution was, I found the bad code path, I found the issue, or at least I found an issue that allowed me to go ahead and resume somewhat normal operation. Well, that's just a fun picture. I had no fun pictures because I rewrote the talk entirely last night. Another issue is once upon a time I had processes that would instantaneously increase to either approximately 2 gigs or would run out of memory. The way we solved this was well, we looked for source code changes and didn't find anything reasonable. Along the way, figured out how to go ahead and use eval Perl code from inside GDB, because again, we're in an adverse, environment, and I don't really know what's going on. So what I was able to do is say, I would like to just call carp and have that print a stack trace on my the standard error for the web server, and that worked. Separately, you can use any arbitrary code inside there. So you can just call perl eval from GDB, and so you can, if you've taken the practice of storing your interesting data that really are globals in just actual globals, then you can access them easily from debuggers. This is an argument for if you have something that's a global, you don't have to use my. If you said our instead, then you get access to it when you're in dire straits. It's interesting anyway. What I actually had to do is I had to dump my entire Perl heap out to a text file and then analyze that to figure out where I had the issue. The way we do the eval in Perl is we just use the eval PV command directly from Perl API. This is in your Perl documentation, and you may read it. The part that is additional here is depending on if you're using a threaded Perl or a non-threaded Perl, you have to pass the thread context. So there's this call to get context, and you won't see that typically in the documentation, or you'll see it as an argument called ATHX. But in this case, this is literally what I can type to go ahead and dump some variable to standard error directly from outside the process. That third argument, 0, is some flag. I don't know what the actual valid values are. I recall 0 is a good default. The unthreaded version is I just dropped the stack context. Sorry, the thread context. And again, I could just write whatever arbitrary things there. However, this is very similar to how unsafe signals work prior to Perl 5.6. So all Perls after 5.6 have a nice coordination. So if you receive a signal, we will wait first for a safe point to actually run your signal handler. In this case, this doesn't wait. So there's going to be some global state in the process we may corrupt. What I'd often find is I can run this command between about 2 times before it totally fails. And generally speaking, I only want to do this to a process that I think is sacrificial. Well, I mean, the context that I've been doing this oftentimes is like websites and all. So oftentimes it's a web request or it's a database request or something that, while I don't want any one person to suffer, someone's going to have to. There are ways around this, of course. So none of this part is actually is productionized in any nice way that I know of, but you can effectively advance the instruction pointer to a safe point as long as you get between Perl instructions. And well, I haven't documented that, so I can't point you at anything for that, but you could figure it out yourself if you were to read the C source code. In terms of actually dumping all the memory contents, Perl organizes all of its memory in a series of data structures called arenas. This is a linked list, and each of these linked lists have a pointer to about 200 or so, 255 Perl values. So to dump all of Perl memory, we just walk that linked list, and for each one, call the dump function on each one, and this goes to wherever the debugging error channel goes, which is usually standard error. So the previous work that I did of calling eval from GDB, we effectively just stuffed this in there and said, okay, great, now my web server will go ahead and dump its entire process memory out to the log file. How I actually found the problem then is a feature. This is a feature of how that works is when it's printing something like an array, it prints all of the pointers on the same line. I think that's not awesome, especially because one of my lines was about 55 gigs and my read line loop also ran out of memory. So this was on my desktop and that was annoying. But once I'd actually figured that out, then I wrote a read line loop that would truncate at 64K and give me something reasonable. And I found an array with a very large index and worked backwards by following the pointers, just opaque things. I mean, you could, if you want to, understand the Perl data structures, or you could just read backwards and keep your intellect around about what's going on. And what I found is this was an array that was captured by a closure, and so this was a cache. And so in this case, the cache was supposed to hold area codes, but it actually held 10-digit phone numbers by accident because of a validation error. A different thing, once upon a time we had an infinite loop. I'm sure you've never had them. In this case, so all the previous steps applied, and they weren't, well, they might have been terribly helpful, but what I ended up doing is I ended up writing some code that allowed me to inject an actual functional debugger directly into the process. So this is a process in production that does not have the debugger. We've installed a debugger after the fact, and we've told it how to send a terminal to my ops person's desktop over telnet and netcat. And that's documented, but effectively the glue for that was eval this code inside my process of load the debugger loader, provide a rendezvous point, and then tell it, yes, please, I would like you to actually stop the process. At that point, we just stepped through the code until we solved the problem. But that was pretty special for me the first time. We had a segmentation fault once. Turned out that through just using the C backtrace, we saw that it terminated in some libxml libraries, and from there just discovered that something had upgraded one of the libxml libraries, and it turns out that libxml.so and libxml, the Perl library, really have to be in sync. So we solved that way. But getting the stack trace from GDB was really helpful in terms of actually understanding where the issue was. Another time, we had a process that grew in memory really quickly. So it would run at a relatively stable rate until something would happen, and then it would just want all of the memory, but not as instantaneously as the previous one. It would just grow very fast. Turns out this was infinite recursion. In this case, I gave my my ops person, here is a GDB script to run to invoke carp on the process when it's in its death throes, which printed off a very long list, and eventually you could see that the frames began repeating a lot. This turned out to be it turned out a template change had caused some mutual recursion. And part of the template system was not in source control; it was a database system. So we couldn't have even found that through our source control auditing. I skipped over briefly this how to Perl stack trace without symbols. That's again that module. While trying to solve this, I came up with this particular module at the time that allowed me to go ahead and solve this because I did not have symbols for production, and mostly that's just by compiling a little bit of Perl code, figuring out what all the reasonable offsets are from everything, and then just walking blindly in the dark, and it seems to work. We're almost done here, but another time, our WebIO was through the roof, and really I just found it by following through strace and seeing where it was writing things from. I found it useful to use a little applet I wrote called IOPS, which just scrapes strace and turns all the relatively inscrutable file descriptor names back into the actual file names, and so I could see where everything was actually coming. It made it humanly reasonable to see where things were actually coming from and going to, instead of having to see 42 and 3 and you can do that, but that's much more work. So, I think the last thing I wanted to say was, after a site redesign, we found that some of our web pages were far too expensive, so we began using the times function call to go ahead and capture what is the CPU cost before and afterwards, so we can capture what is the user CPU. That allowed us to triage what are actually CPU expensive web pages were. Later on in the process, we'd turned on devel NYT-prof for a single process in a multi-forked Apache, mostly just by asserting that one of the processes was going to have they were all going to acquire a lock, and only one of them would win. Anyone who didn't win just started up normally. The other one would go ahead and load it NYT-prof. That's 20 minutes. Any questions we have, I think?
You talked about the save point where you can actually step into GDB.
Yes.
And then call the eval and so on. So I think the built-in threaded environment to get context, you can just replace with micro, but that's a global ruling context.
I don't know. So the question was, when you're dealing with the safe points in a threaded Perl, and can you just use my Perl? Part of this is something dealing with p-threads and whatever that context is, and I don't understand it well enough to answer that.
Yeah, p-threads, okay, different. You can check with your topic. But the save point would be in the one loop. In one C, just the one loop, because then the registers are saved, and then you can safely call any PP function. Otherwise, it works normally.
Yes.
aside from look at the source code, do you have a set of first steps that you tend to always use in order to narrow down on the problem?
Top, netstat, LSOF. If those don't get me anywhere, strace, GDB backtrace. Those are actually, those generally speaking don't impact the process as much at all. Things that GDB just for backtrace and GDB just for strace both use the same method, p-attach, and that slows the process down some. So I don't want to run it all the time, but it's really safe as far as I understand it anyway. Anyone else? Do you recall what kind of problem it was? The segmentation fault? It was libxml? Oh, I'm sorry. All right, I'll leave the slide there then. Yeah, it's the libxml libraries tend to be fairly tightly bound in their versions. So if you upgrade either your C library or the Perl library by any amount, you have to make sure you're actually within the constrained window that's safe for that, is all. It's fairly specific, but it's a nice example of how just looking at a C stack trace can give you something useful to look at. Okay, so the question was for how did we actually find out that it was the version issue? I don't recall exactly what happened during our debugging process for deciding that it was actually a version incompatibility issue. It might have been just someone in the office was looking at documentation enough and came across that there was a version incompatibility issue. Or someone might have actually just looked at the dpackage log. I mean, that's my recollection. Yes.
So I'm familiar with LSOF, but strace and all this stuff. But GDP, I'm not that strong on.
Yes.
What tools did you use to learn more to develop those skills?
I started by learning C code, how to program in C, and then I read the manual.
No, but I mean GDB in particular. It's just because your background in C.
I started. My background starts in Perl, then goes to C, and so I learned more C code, so I could do more interesting Perl code. And then I read the manual several times.
And there's a stack of questions about GDB. There's one or two of those that go into detail about the usual commands that's used to look at.
Yeah. I mean, the easiest, best thing to do is just start with backtrace. I mean, there are other interesting things you can do in terms of examining raw memory, or you can call raw functions, which you can see that I've done in these examples. I mean, that's effectively canned. You can just copy and paste that without having to read the manual for that. But you know, it's also good if you do. Hello.
Yeah, so I just wanted to clarify. So pystack and app-stacktrace will give you the GDB command necessary to produce a backtrace in the scripting language that you're working with.
It produces a script in the GDB script language.
Right. That gives you a Python backtrace?
Yes. I mean, so pystack gives you a Python stack trace for the actual language, similar for the Perl version as well. Yeah.
So it's constructed from all the Python stack frames.
Yes, that's true. I mean, yes, it's one way. So the Perl code, the way that it works is it actually just does dead reckoning by following a pile of pointers around. However, another way that it has worked in the past, a different version, actually says, great, let me go get an array and let me use the array API to follow that to the next element and move that around and actually use, follow all the symbols normally. So, I mean, it's duplicating your AC stack trace dumping thing in a more restricted language that still has much of the same power. Okay. Thank you. And should you need the URL, well, there it is.